Welcome back. This video is going to talk about a different type of interval called a prediction interval. And let me just mention that these intervals will come back to us when we do regression analysis and be, I think, very important when we get to that chapter. But I think they're much easier to understand here when we're just talking about a single mean. So let's talk about prediction intervals. I'm going to assume that I have a random sample of size n from some normal population. Now, unlike confidence intervals where we've got the central limit theorem working for us, normality is really important here. So we need to be checking our normal probability plots even if we have massive sample sizes when we compute a prediction interval. So we have a mean of mu, and a variance of a single observation is just sigma squared. Now, confidence intervals allow us to make inferences about the mean. Instead of making inferences about the mean, prediction intervals describe the uncertainty of a single new observation. Okay, so with confidence intervals, I want to find a window where I think the true mean lies. With a prediction interval, I'm trying to find a window where the next observation is likely to fall. And in fact, I want to quantify how likely it is to fall as being with probability 1 minus alpha. All right, so I'm going to be labeling this new observation, the next case we observe, as an x naught. So that's just a single x. Here's a very short example that we'll solve in a minute, but let's say I'm very interested in how much caffeine is in a cup of coffee. So I randomly sample 12 cups of coffee, I measure the caffeine in there, and we find the x bar is a certain number, standard deviation is a certain number, but I don't really care about the average amount of caffeine in a cup of coffee. What I'm more interested in is I'm going to go make myself a cup in a minute, and I want to know how much caffeine is going to be in my cup of coffee. So I don't care about the mean, I care about my cup of coffee. All right, so let me begin by saying that if we knew mu and sigma, the problem would be easy. So let me just go over to my document camera for a second and just prove to you that this is in fact easy. So let's look at the distribution of x. Now, whenever we've been doing confidence intervals, we've talked about the distribution of x bar. Here we're going to talk about the distribution of x. And I've assumed the distribution of x is normal. The mean of this distribution is mu, and the standard deviation, well, the variance of x is sigma squared. So what we know is, let's just say I have an x naught from this population. So normal mu sigma squared. So I'm going to standardize this x naught. So we can say that z is equal to our x naught minus mu divide by sigma. And so here's a true statement. I'd like to have a window. So where I have 1 minus alpha in the middle, we'll stick alpha by 2 in either tail. So here's a true statement. 1 minus alpha is equal to the probability that negative z alpha by 2 is less than this z thing, so I've just made myself a z statistic, is less than positive z alpha by 2. So for example, if this is 1.96, well, if I want 95% in the middle, this would be 1.96 minus 1.96. And so the probability that I have a z statistic between minus 1.96, positive 1.96 is of course 95%. All right, so let's go do a little bit of math on this. I'll multiply all parts of this inequality by sigma, and then I'll move mu from the middle to the outsides. So mu minus z alpha by 2 sigma. So if I go, 2 standard deviations to the left of the mean, and I go 2 standard deviations to the right of the mean, so that should be a z, sorry about that, z alpha by 2 times sigma, then I have 95%. So the probability some observation is within 2 standard deviations of the mean is 95%. Now I've got a bit of a problem here because first off, I don't know mu. And secondly, I probably don't know sigma. So if I go do the usual thing and plug in an x bar here and I plug in an s there, I have additional uncertainty. So the way everything I've done so far is assume that these are known constants. But if I stick in random variables here, what's going to happen? Well, there's going to be a lot of additional uncertainty that's not accounted for by this statement. So let's think about the distribution of x naught minus x bar. So let's just establish a few properties about this. What's the mean of this thing? So the mean of this is just the expected value of x naught minus the expected value of x bar. And so what is the mean of x naught? Well, it's mu. What's the mean of x bar? Well, that's also mu. So on the average, this the difference between an observation and the sample mean ought to be 0. What's the variance? Well, the variance of x naught minus x bar is going to be, these are independent of one another because this observation is independent of the n observations that make up x bar. This is just going to be the variance of x naught. And then you can think of there being plus a minus 1 in front of this. That minus 1 gets squared when I distribute this variance operator. So it's going to be plus the variance of x bar. So what is this? This is just sigma squared. That's assumed up here. What's the variance of the sample mean? Well, the variance of the sample mean is sigma squared over n. So I can factor out a sigma squared, and I'm left with 1 plus 1 over n. Finally, the distribution of this statistic, so x naught minus x bar has a normal distribution. And the reason I know that is this is just a linear combination of a bunch of normal random variables, and therefore it's still normal. So remember I said this is normal, and we're not going to relax that at all. All right. Now, if I know sigma squared, then we know that this is a z. So x naught minus x bar. Now, if you want to be really precise, we would write minus 0. So 0 is the mean, but if you don't want to write that, that's fine. And divide by the standard deviation of this thing. So the standard deviation of this thing is sigma times the square root of 1 plus 1 over n. So we know that this is a z statistic. If we don't know sigma, then we can make a t statistic as follows. A t would just be x naught minus x bar, and if you want to subtract the 0, you can. And this would be s times 1 plus 1 over n. All right, so we'll work with whichever one you like. Let's take this one. So we can go make a 1 minus alpha interval by saying this. This is of course equal to negative z alpha by 2 less than, well, x naught minus x bar divided by sigma over 1 plus 1 over n less than z alpha by 2. Now we're going to do some similar manipulation. I'm going to multiply all three sides by this thing, so that would cancel out in the middle. This is a positive amount, so it doesn't change the sense of the inequality. After I do that, I'm going to move my x bar, so let's add an x bar to all three parts. So this is equal to the probability that I have x bar minus z alpha by 2 sigma times 1 plus 1 over n. Okay, less than my x naught less than x bar plus z alpha by 2 times the standard deviation 1 plus 1 over n. And so this quantity is my prediction interval. So it's giving me a window where there's a probability 1 minus alpha chance that my next cup of coffee is between those two values. So another way to write this is it's just x bar plus or minus z alpha by 2 sigma 1 plus 1 over n. So that's the formula for a prediction interval. Let's go back to the course packet for a second. So I just, I did it for the z, where we know sigma. If you do it with a t, where you have an s, you end up with the same formula, except there's an s and a t rather than a sigma and a z. As far as I know, there is no function in R or library that I know of that does it, but we don't need it. We can just write it out by hand. So let's go back to my coffee problem. My coffee problem, I observed 12 cups of coffee, measured their caffeine, found that mean, that sample standard deviation. So let's just take the mean. This is how you do a plus or minus in R. So just take a vector minus 1 plus 1. Let's find the 97.5 percentile of a t-distribution with now 11 degrees of freedom, times the sample standard deviation, times the square root of 1 plus 1 over n, or 1 plus 1 over 12. And there is my prediction interval. So let's think about what this is telling us. It's telling us that there is a 95% chance that the next cup of coffee that I make is going to have between 72 and 128.6 milligrams of caffeine in it. What happens when n goes to infinity? So when n goes to infinity, what's going to happen is 1 over n will go to 0, and this term will approach 1. So what am I left with? Well, I'm left with x bar, which will converge to mu with large enough sample sizes. My s will converge to sigma, and my t-distribution becomes arbitrarily close to a z. So I'm just left with basically mu plus or minus my z times sigma, which is what I would have if I knew mu and sigma in the first place. Okay, so that's kind of reassuring. Just a few more things. We can do one-sided prediction intervals if we want. So instead of splitting up the alpha into the two tails as we did before, we stick all the alpha in one tail. So here I have alpha by 2. Here I have all alpha in one tail. So let's just do a couple problems. Let's say I'm only interested in the lower bound for this. So the caffeine is at least some amount. So let's go find a one-sided 99% confidence interval for the mean. So if I did that, take our mean minus, here's my 99th percentile of a t-distribution with 11 degrees of freedom, and I'm going to use s over root n. So think of this as S over root n. And so the confidence interval would be from 90 up to infinity. If I wanted to find the same 99% one-sided interval, but this time make it a prediction interval, what I'd like you to note is my formula is identical, except for one thing. I'm going to multiply by the square root of 1 plus 1 over 12 rather than just the square root of 1 over 12. Alternatively, if I wanted to find a two-sided 99% confidence interval, well, I would just change this to the 99.5% percentile, and I would get the correct answer. All right, that's it for prediction intervals. I would ask that you now go do some problems in Devore.